Boas noites, benvidas a todas e benvidos a todos. Estamos na sexta semana da ciencia, xa hai 6 anos ou 5 anos que comezamos a facer estas xornadas con cada vez máis actividades. Polo que se ve hoxe, estamos todos moi contentos de ver tanta xente hoxe para ver esta conferencia, pois tamén con máis repercusión. Como probablemente sabedes, temos toda unha serie de actividades que incluen concursos científicos. Onte tivemos unha Nerd Night, hoxe temos a conferencia. O Instituto Galego de Física de Altas Enerxías existe desde hai 24 anos, o ano que ven vamos cumplir 25, pero tivo un cambio, vexo bastantes físicos aquí, tivo unha transición de fase hai como 6 anos. Desa transición de fase xurdiu pois as Semanas da Ciencia que estamos organizando, pero tamén moitas outras cousas, e entre elas un aumento moi grande da nosa actividade e tamén da xente que traballa no Instituto. Para o ano que ven vamos ter, se non hai demasiados retrasos cas obras, unha nova sede, e seguramente xa poderemos facer moitas das actividades da Semana da Ciencia que temos un pouco espalladas por moitos sitios, algunha delas xa na nosa sede. Non esta conferencia, porque non vamos ter un sitio tan grande, pero sí que poderemos facer moitas actividades. Bueno, quero agradecer que viñesedes todos aquí, pero quero agradecer en particular a presencia de Borja Berea, que está pois en representación do Grupo Popular no Concello. Creo que boa noticia tamén que os representantes públicos e os que eventualmente teñan que decidir sobre o noso futuro que se interesen pola ciencia. Quero agradecer especialmente a Krishna, que vai falar agora, a súa presencia aquí. So thanks, Krishna, for coming. I hope you have enjoyed the stay here, and I hope you also enjoyed your talk, and not only us enjoying your talk. Entón, Krishna Rajagopal é profesor de Física Teórica no MIT. Fixo a tese con Frank Wilczek, que é un premio Nobel de Física polo descubrimento da liberdade asintótica. Un dos seus primeiros traballos, non durante a tese, pero pouco despois, foi a proposta dun novo material, que é un novo material que se chama un superconductor de Quark. El vai nos explicar agora de que vai todo isto, pero a idea é que cando dentro dos protóns e os neutróns temos quarks e gluons, e cando poñemos moito xuntos a alta temperatura, creamos materiais novos. Estamos fabricando este material, agora mesmo acabou xa ahorrando LHC, pero a semana pasada estábamos fabricando este material moitos millóns de veces todos os días. O único problema é que dura moi pouco tempo, uns octosegundos. Moi pouco tempo, vale? Este material pode estar nestas colisións que estamos creando, e aí estamos identificando cal son as súas propiedades, pero podería estar tamén, por exemplo, no centro de estrelas de neutróns. E isto foi unha das propostas que fixo Krishna, e unha cousa que está estudando agora neste momento, que no centro no corazón das estrelas de neutrón, no interior das estrelas de neutróns, pode haber este novo material, que é un superconductor de Quark. Seguramente escoitastes estes días noticias sobre descubrimentos do material no interior da Terra, a composición do interior da Terra. Bueno, pois, aparentemente, vamos ser capaces, dentro de pouco, de identificar tamén materiais novos dentro de estrelas de neutróns, o cal parece unha cousa bastante de ciencia ficción, pero é así. Entón, bueno, non me vou enrollar máis, que xa me enrollei bastante. Presento vos a Krishna Rajagopal. Despois da súa intervención vades ter tempo de facer todas as preguntas que queirades. So thanks, Krishna. So the floor is yours.
Thank you very much. So thank you very much for the very kind introduction. And it's been a real pleasure to visit Santiago de Compostela for the first time. We've had a great visit, and I look forward to coming back many times in the future. As I will say later on in the talk, the scientific group working in this field here is world leading. That's a point that I will make much later in the talk. So 50 years of quark matter, from protons to hot Big Bang soup and back. The talk that I'm going to give, why is this not responding? Just a minute. There we go. Okay. The talk that I'm going to give is a part of the answer to two kinds of questions that many of us ask already when we're children. One of those questions is, what's this stuff made of? You pick anything around, you take a glass of cup of coffee, what is it made of? And someone tells you it's made of water molecules with caffeine. Well, what's that made of? And what's that made of? And what's that made of? And what's that made of? Always trying to ask what is, go down to the next level. And very important also then, how do the bits fit together? How do the water molecules and the caffeine molecules make up coffee? How do the atoms make up water molecules? This is one of the kinds of questions that go back to childhood. In an illustration, you take any chunk of matter, what's it's made of? It's made of molecules. What are those made of? They're made of atoms. What's the atom made of? Electrons and nuclei. What are the nuclei made of? Protons and neutrons. What are they made of? Quarks. And I'll be talking about the left half of this diagram, starting from atoms and working the way to the left. The second question, again, that many people ask as children is, well, where did this stuff come from? What's the origin of the Earth? What's the origin of the sun? Where did it come from? And you keep going further back. Where did the first atoms come from? Where did the first protons come from? Where did matter come from? So what's the history of the universe? And I'll come back to this slide at a later point in the talk, because I'm going to start with the first question and come to the second question later. But the story of quark matter that I'm going to tell, the 50-year history of quark matter, fits into both of these themes. What is matter made of? And how do the bits that make up the matter, how do the bits make up the whole? And where did everything come from? Where did protons come from? Where did atoms come from? And we'll come to that second question a bit later. Where I want to start is, what are atoms made of? And by around 1905, so 120 years ago now, it was well known that atoms were made of a cloud of electrons, and that they were negatively charged. But atoms were neutral overall, so there has to be positive charge somewhere. And it was thought at that time, say around 1905, that the positive charge was smeared throughout the volume of the atom, and J.J. Thomson famously called it a pudding. So there was a pudding of positive charge with the electrons embedded in it. That was J.J. Thomson's model. That turned out to be incorrect. How did we learn it was incorrect? We learned it was incorrect from experiments done in 1909 by Geiger and Marsden. Geiger and Marsden were the young students, maybe they were the analog of postdocs today, working with Rutherford. Rutherford is much more famous than Geiger and Marsden, but I'm telling you the experiments were actually done by Geiger and Marsden, understood by Rutherford in 1911. These experiments completely contradicted Thomson's picture. And so what Rutherford, Geiger, and Marsden discovered is that the positive charge is not a pudding. It's a very, very small thing at the center of the atom, much, much, much smaller, in fact, 100,000 times smaller than the atom itself, called the nucleus. And how did they discover this? What kind of microscope did they use to make this discovery? This discovery is famous for the discovery of the nucleus, but it's just as important that this was really the first time that scientists looked at matter in a new way, and this then new way of looking at matter has been used over and over and over again, and will appear 3 times today. And what Geiger and Marsden did on Rutherford's suggestion, we'll start in the bottom left here. They took a gold foil and shot a beam of alpha particles through it from left to right, and what they were expecting to happen is, what What they were expecting to happen is shown in this cartoon on the left. They were expecting that these alpha particles would go through the gold foil and would be deflected very, very slightly so the beam spreads out a bit, because after all, they're just these were going through this pudding, and the pudding couldn't really stop the alpha particles or deflect them very much. That is not what they saw. They saw that, well, many of the alpha particles went straight through, but some of them bounced off, and some of them even bounced backwards. Rutherford famously said that this was as surprising as if you had shot a cannonball at a tissue paper and it had bounced back. And from this fact, Rutherford correctly concluded that all of the positive charge and most of the mass of the atom is in this very, very small thing in the middle, which is the nucleus, which he discovered. So he saw nuclei. What do we mean when we say we see something? We shine light on it. The light scatters into our eyes. We see with our eyes. We say we've seen something. Same idea here. They shone alpha particles on it. The alpha particles scattered. They didn't see them with their eyes. They saw them with a fluorescent screen here. By the way, this whole apparatus was about this size. This small, much smaller than what you see on the screen. And so that's the discovery of the nucleus. By around 1911, from this discovery, atoms feature a cloud of electrons, but they're around a positively charged nucleus. The size of the atom is around 10 to the minus 10 meters. The size of the nucleus is 100,000 times smaller, so 10 to the minus 15 meters roughly. And to be more precise, by the 1930s, more had been learned via similar experiments that I won't describe in detail. Nuclei were known by the 1930s to be made of protons, which had charge +1. Maybe the blue balls here represent protons. Neutrons with charge -1. Think of the red balls as neutrons. And what was known, again, by the 1930s was that each of these objects, protons and neutrons, were about 10 to the minus 15 meters in size. That scale is going to be very important in this talk. The size of the proton, the size of the neutron, it happens to be about 10 to the minus 15 meters, and it is 100,000 times smaller than the size of an atom. So where we are in this cartoon, as we're working our way from the right to the left, we are at the diagram second from the left, protons and neutrons. And, well, what are protons made of? Keep going. That childlike question, well, what's that made of? What's that made of? What's that made of? So what are protons made of? By the 1960s, this was the great question. Trying to answer this question in the 1960s was profoundly confusing. By the 1960s, protons and neutrons were not the only such particles known. There were dozens and dozens of short-lived cousins of the proton that had been found. For those of you who came to Nerd Night last night, Jose Edelstein did a wonderful job of describing what I'm here calling the cousins of the proton. He gave them their scientific names. I won't. All I'm telling you here is that their charges can be +2, +1, 0, -1, or -2. They have many, many different masses. Everyone has a different mass. But they all have the same size. They don't vary in size, which is important. What Jose told those of you who came yesterday evening was that their masses came in patterns and their charges came in patterns, sort of like a periodic table. And by this time in the 1960s, people, by looking at the patterns, had done what Mendeleev had done, which was to draw inferences about what protons must be made of. And they had figured out that the patterns suggested that they were made of something smaller, which were named quarks. Up quarks, down quarks, and strange quarks, U, D, and S from yesterday, with charges +2/3, -1/3, and -1/3, also antiquarks with the same mass and opposite charge. It was as if protons were made of a U, and a D. We can just add up the charges. U is 2/3, D is -1/3, 2/3, 2/3, -1/3, that's 1. And it was as if a neutron was made of a U and a D and a D, and that's charge 0. Some of the proton's cousins were as if they were made of 3 antiquarks. Some others of the proton's cousins were as if they were made of a quark and an antiquark. Jose described this in more detail yesterday. But why only as if? When Rutherford and Thomson were talking about electrons, they knew that you could pull an electron out of an atom. And we know that also. Every one of our electronic devices, my phone, which is on the stand over there, my laptop, this pointer, everything that we use in modern technology, there are electric currents flowing through the circuits. Those are electrons that have been pulled out of the atoms. We know how to pull protons out of atoms. So you can take an electron out of an atom and look at it just by itself. But as of the 1960s, nobody had ever succeeded in kicking a quark out of a proton and looking at it by itself. And in fact, to this day, nobody ever has. So you had this very strange situation that the patterns suggested that protons and neutrons were made of quarks, but nobody had ever been able to pull a quark out of a proton or a neutron. The key next step was at the very end of the 60s, 1968 to 70, Jerry Friedman, Henry Kendall, and Richard Taylor, they were the first people to try to answer this question Rutherford style. You want to see what's in the proton? Try and bounce a projectile off what's in the proton to see what's in there. The projectile, instead of being a naturally occurring source of alpha particles, was a human-built accelerator at Stanford in California, 3.2 kilometers long, much bigger science than in Rutherford's day. It accelerated a beam of electrons to a very high energy and slammed it into the protons. And Friedman, Kendall, and Taylor, what their cleverness was to repeat what Rutherford had done and to say, let's look for large angle scattering. Let's set up an apparatus to look and let's see, will the electrons scatter at large angles? This was not popular at the time. It was not what people were looking at that time. Other people were not doing this at the time. It sounds obvious to us. Do the Rutherford experiment. That's what you should do. It's obvious with hindsight. It was not obvious at the time. And one of the reasons it was not obvious is that if you take a proton and you shoot an electron at it, and the electron bounces off at a very large angle, and this electron has this enormous energy, it blasts the proton into smithereens. And how are you going to study the structure of a proton by blasting it into smithereens? Smithereens, what are smithereens? Smithereens, in this case, are a jet, a spray of many proton cousins. So you slam the electron into the proton, you blast it into many, many, many particles, and the electron scatters at a large angle. How could that be an interesting experiment? Well, Friedman, Kendall, and Taylor did it. And just as Rutherford had done 60 years earlier, this is a cartoon of their apparatus. The electron beam comes in from the left. The hydrogen target is labeled here. The protons are there. Electron beam comes in from the left. And you can swing these cameras around on these arcs. And so you can look for scattering at this angle or any other angle where you can put those cameras. The cameras are not this size anymore. This is an actual picture of the cameras used by Friedman, Kendall, and Taylor in 1968. And you see a person down here for scale. So these cameras are much bigger pieces of apparatus. And what they saw was what Rutherford saw. Once in a while, an electron hits a quark, we now know. Once in a while, an electron hits a quark, and the electron comes off at a large angle. And by looking at the angle at which the electron comes off, you're able to learn about the momentum of the quark inside. In fact, you're able to learn about the quark inside. And yeah, you blast the proton into smithereens. That up quark that you just hit, you blast that with such energy, you destroy the proton, and you make a smithereens off to the right. The technical term for the smithereens is a jet of particles. So what are protons made of? Friedman, Kendall, and Taylor saw quarks. They saw quarks just as much as Rutherford saw nuclei. They saw quarks. Quarks are now real. They're not as if, they're real. They saw them. Quarks inside a proton just as real as nuclei inside an atom. When you bounce a very high energy electron off a quark, in the proton at a large angle, I'm not giving you any equations in this lecture, but the scattering is quantitatively just as if there were point-like quarks in there. For those of you who are in Jose's talk, the person who realized what quantitatively means here was James D. Bjorkane, whom I didn't put on the slide but should have. Sounds great, but in a sense, this completely just made things even more confusing. Quarks are real. You can see them the same way Rutherford saw nuclei, but you can never see one by itself. Still to this day, nobody has kicked a quark out of a proton and seen a quark by itself. So what is going on? So what are protons made of? Clarity finally came in 1973, which is 50 years ago. So the 50 years in the title is because it was 50 years ago that scientists finally figured out what was going on with this what are protons made of question. Gross, Wilczek, and Politzer discovered the laws of nature that govern what we call QCD. I'm going to slip at times and use that phrase. I will try not to. QCD are the laws of nature that govern how quarks behave. I'll try to use language like that. And Gross, Wilczek, and Politzer discovered the equations, discovered the laws, discovered the fundamental laws of nature that govern this aspect of the world around us. This is just as important as what Galileo, Newton, and Einstein did for gravity, or what Coulomb, Ampere, Faraday, Maxwell, Feynman, Schwinger, and Tominaga, some of those names you recognize, some you may not, what this sequence of scientists over more than 100 years did for electricity, magnetism, and light. In all those cases, finding the fundamental laws that govern the natural phenomena in question resolved prior confusion. In the case of the 1973 discovery, what they got was a quantitative description of all known phenomena involving quarks, which is amazing. This is a core part of what we now call the Standard Model, which is a terrible name. It should really be called the theory of all matter. And the point of today's lecture is to, first I'm going to tell you how the confusion was resolved. I won't leave you hanging. I'll tell you how the confusion was resolved. But really I want to go on, and anytime, whether it was Einstein discovering the fundamental laws of gravitation or Maxwell discovering the fundamental laws of electromagnetism, when you discover something fundamental, you get out more than you put in. Einstein was not looking for gravitational waves, but his equations predicted them, and 100 years later they were discovered. Maxwell was not looking for electromagnetic waves, but his equations predicted them, and about 20 years later they were found by Hertz. Friedman, Kendall, Taylor, Gross, Wilczek, Politzer, Bjorkane, they were not looking for quark matter, but the equations predicted it. These equations open new vistas to scientific investigation, and that will be the main part of the talk. But to finish the introduction, I want to answer the question of what are protons. Well, the protons are made of quarks and gluons. And quarks and gluons are not so different than electrons and photons. Electrons we've met before, they have charge. And any charged particles interact with each other by exchanging photons. Photons are particles of light. Light is made of photons alone and is governed by Maxwell's equations. The facts that I just described have been known since some part of the Maxwell's equations since 1864, and that light is made of photons alone since the early 20th century. What about quarks now? Well, quarks have a new kind of charge. Electrons have electric charge. Quarks have QCD charge, which was named color. Color is a new kind of charge. That's the word that people started to use in the mid-1960s. Electrons are charged, quarks are colored. Any colored particles interact with each other by exchanging gluons. So quarks interact with each other by exchanging gluons. That sounds the same. The only difference, and gluons are governed by equations that look a lot like Maxwell. The only difference is that the gluons themselves are colored, so gluons can exchange gluons. I've tried to walk you through this slide in a way that sounds boring. Okay? This sounds like a technicality. It sounds like these laws are pretty similar to what describes light and electric currents. But what Gross, Wilczek, and Politzer showed is that the laws that they discovered are in fact very different and have remarkable consequences. So to explain, let me compare and contrast the force between electrons to the force between quarks. Going back to Coulomb, about 200 years ago, the force between electrons is proportional to 1 over their separation squared, 1 over r squared. That means as r goes to 0, the force gets larger, like 1 over r squared. What about quarks? Well, what Gross, Wilczek, and Politzer showed, and this is the asymptotic freedom that, in fact, Carlos mentioned in his introduction, is that as quarks get closer together, the force between them grows more slowly than Coulomb. So quarks interact weakly when they're close to each other, weaker than Coulomb. What about if you pull quarks apart? Well, if you pull quarks apart, at first, things don't look so different. But what Gross, Wilczek, and Politzer discovered, we now, and as many others learned to use these equations, is that when the quarks get to be more than a certain distance apart, the force between them stops falling off. I have a rubber band in my hand here. I can feel a certain force. Now let me move my hands further apart. It's the same force. It's the same force. It's the same force. It does not fall off, even though I just tripled r. So the force between quarks, once they get further apart than some capital R, doesn't fall off anymore. So the forces between quarks get very strong when they're farther apart than capital R. So hidden in these equations, there's a new scale of nature. It's capital R. Well, how big is it? It's about 10 to the minus 15 meters. So these equations have in them the size of the proton and the size of all of its cousins. So the reason that all of the proton's cousins have the same size is because their size is all set by the distance when the force becomes strong. So now, I think this was either in Jose's talk or in Carlos's talk yesterday. If you imagine slowly pulling farther and farther apart, I'm not going to do it because this is my wife's exercise device, and she wouldn't want me to break it. But if I pull it apart far enough, it will break. I won't do it. And you're supposed to think of the quarks as like the ends of the rubber band. So right now, this rubber band has 2 ends. My hands are holding them. If it breaks, it'll have 4 ends. As soon as it breaks and I have 4 ends, then I have 2 cousins of a proton. I have one in my right hand, one in my left hand. They're completely separate. I have 2 quarks and 2 antiquarks instead of just 2 quarks. Instead of just 1 quark and 1 antiquark. That's not what actually really happens in the experiments I was describing. A better way of thinking what happens in the experiments I was describing is this hand is the quark that the electron from the Stanford Linear Accelerator hits. Okay? And that electron has been accelerated for 3 kilometers. It is coming in with an extremely high energy. It clobbers this right hand of mine, kicks it with enormous energy off in that direction. And as it does so, this rubber band shatters. It doesn't just split in 2, it breaks into 10 pieces. Each one of those pieces is a cousin of the proton. And that's how you get a jet. This is the picture that emerged from the equations that Gross, Wilczek, and Politzer discovered. The rubber band is safe. And so I'm not writing the equations down for you tonight, but the laws of QCD are precise and predictive. They immediately led to understanding of some things, like why are all the cousins of the proton the same size? Understood immediately. Why were Friedman, Kendall, and Taylor able to see quarks? Well, when you clobber a proton with an electron the way they did, what you are doing is you are resolving one quark deep inside a proton where they are weakly interacting. It is what their experiment. It is as if you have a camera. It's a 3 kilometer long camera, but you have a camera that is taking a high resolution photograph with a very fast shutter speed of where one quark in the proton happens to be at one moment. That's what that experiment is. It's very Rutherfordian. Yes, you had to destroy the proton to answer the question. So be it. So there were some things that were immediate. They were understood in 1973, boom. But the equations used to describe these laws are in fact fiendishly difficult to solve in full. And anything that corresponds not to extremely fast photographs is very hard to calculate. And one thing that is an example of that is, well, what's the mass of the proton? I said these equations describe everything that quarks do. They should describe the mass of the proton, and they do. But it took until 2008 to learn how to solve the equations. It took the development of new algorithms, new advances in computer science and theoretical physics, and in faster computers. But by 2008, the equations that Gross, Wilczek, and Politzer wrote down in 1973 made a prediction for the mass of the proton, which is the prediction in red here, and it agreed. Sorry. It agreed with what was measured, which is the black number here. Same for this cousin of the proton, this one, 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 this one. And there were even predictions for much more subtle mass differences. And this is the best example of something that was calculated before it was measured. The measurement was done, everything agreed. So by this time today, we now know how to solve the equations to calculate some things, not everything. And QCD describes all phenomena involving quarks. And it is central to the description that quarks behave differently when you look at them with a fast shutter speed versus if you look at them over long time scales. Okay, so that's the end of the introduction. We're at 1973 now. New fundamental laws of nature discovered, and anytime that happens, it opens new vistas for exploration. And already by 1974, Collins and Perry had realized that if you could crush a star's worth of atoms by a factor of about 100,000, you would crush all the empty space out of the atoms and crush the protons and neutrons on top of each other and crush them into each other and make a soup of quarks. And in fact, if you read their 1974 paper, they called it quark soup. This quark soup is what Carlos was talking about that later than 1974, but earlier in my career, I helped to understand its properties, although I'm not planning to talk about that today. How do you make such matter? Well, you have to look at a neutron star. There's nobody in the laboratory has a piston that can crush atoms by factors of 100,000, but nature makes such a piston. It's called a neutron star. Neutron stars have a mass roughly that of the sun, but they're 100,000 times smaller than the sun. So they crush the matter in their centers to these densities, maybe. This slide represents a very exciting area of scientific exploration. This is the first of, I think there might be 5 examples in the rest of the talk where I could give an entire lecture on this slide, but I had to pick. So there's increasing evidence that neutron stars with masses about twice that of the sun may have quark soup in their cores. This is not yet established, subject of active research. I decided, instead of talking about the possibility of cold quark soup in the center of neutron stars, which might be there, but we don't know, I instead decided to talk about hot quark soup, which we know exists today in a certain context, and which we know existed everywhere in the universe at the beginning of the Big Bang. This also goes back almost to 1973. It's hard to point to one paper because there are lots of people doing lots of parts of what's on this slide. But by the mid-70s, it was clear that if you could create high enough temperatures, protons and neutrons cannot exist. At high enough temperatures, matter cannot be made of protons and neutrons. The protons and neutrons, if you imagine them at this high temperature, they'd be slamming into each other at such high energies that they would fall apart. That's one way of saying it. Another way of saying it is that above a temperature which is somewhere around 2 trillion degrees, that's so hot that there are many, many, many quarks and antiquarks and gluons in the volume of what would be a proton. So there's no chance for a proton to exist. This stuff was understood to be a gas of colored particles. After all, very high temperatures. Quarks are all close together, weakly, point-like Freeman Kendall Taylor. And a gas of quarks and gluons. The only place in time where such temperatures arose in nature was, well, everywhere throughout the universe, but for the first 10 microseconds of the history of the universe. So all of a sudden, via these laws that Gross, Wilczek, and Politzer wrote down to describe the mysteries that I introduced earlier, all of a sudden we have a chance to answer the other kind of childlike question. Where did matter come from? How did the first protons form? So let me come back to this diagram. This is obviously a cartoon of the history of the universe. We today are here on the right. You go back in time to the left. Here at this time of around 400,000 years after the Big Bang, we live 13 billion years after the Big Bang. This is 400,000 years. This is where atoms formed. Earlier than 400,000 years, atoms don't, it's too hot, atoms can't exist. You have nuclei and electrons, but they haven't bound into, they're not yet bound into atoms. That happens here. Somewhere between this cartoon and this cartoon, this is where nuclei form from protons and neutrons. That's at about 3 minutes. Somewhere between here, which is 10 to the minus 4 seconds, and here, which is, let's say, 10 to the minus 6 seconds, you go from having, well, the people who made this cartoon drew a gas of quarks and gluons. Here we have protons and their cousins. So because we have the laws of nature now that describe quarks, we know that protons and neutrons can't exist earlier than 10 microseconds. It's impossible. And, well, it's obvious that what you must get is a gas, right? I'm trying to tell you by my voice that that shouldn't have been so obvious. But one of the reasons why we all, including me, were seduced into thinking that what we would get at these very high temperatures is a gas, is calculations like this that were done with the same kinds of supercomputers that were used to calculate the mass of the proton. This is a calculation from 2010 of the energy and the entropy of quark-gluon plasma. And what you see is that there's this temperature right about here. This is 2 trillion degrees right here, or right here. Whoops. Something dramatic changes in the world when you get above 2 trillion degrees. And the top of each of these graphs represents a gas of quarks and gluons. And when I teach physics to second-year undergraduates, they can calculate the energy and the entropy of a gas of quarks and gluons. It's a very, very easy calculation. The people who in 2010 used supercomputers to do the real thing, what they got was about 20% less. So, well, it's pretty close to the gas, right? It's within 20% of the gas. The lesson of history here is you shouldn't try to infer dynamical properties from things like energy and entropy, which are static properties. The way this stuff behaves is very different. So we now come to the question of what are the dynamics of hot quark matter? This putative gas. What's it actually like? How does it behave? How does it move? How does it flow? These questions were not answered until scientists reproduced this stuff in the laboratory. So today, in Geneva and Brookhaven outside New York City, scientists accelerate and collide heavy nuclei, and they are recreating the Big Bang. Not in the whole universe, in a tiny little spot where 2 nuclei collide, they are making matter, which is more than 2 trillion degrees hot. They're recreating little bangs. They're small. They're the size of a nucleus, not the size of a universe. It was already clear back in 1983 what energy you needed. What was the energy you needed to reproduce hot Big Bang matter? Busha and Goldhaber calculated this in 1983 based on experimental data that I won't explain. I'm also not going to explain the units, GeV. GeV is an energy unit that I'm going to use many times in the next few slides. You need 100 units of energy. It's a very, very high energy. 100 if you want to make hot quark soup. In 1983, that was impossible. The best accelerators were almost a factor of 100 weaker than what was needed. But in the year 2000, an accelerator outside New York called RHIC, the relativistic heavy ion collider, achieved collisions at 200 GeV energy, twice what Buja and Goldhaber had said was necessary. And today, outside Geneva at CERN, the Large Hadron Collider, LHC, achieves energies of 2,700 to 5,000 GeV. So these two machines are recreating little bangs. These little bangs really do reproduce the hot stuff that filled the universe, but in a very small volume, and that little droplet of extremely hot stuff explodes. It doesn't, there's no walls. You do a collision, you make a drop of very, very, very hot gas, question mark, very, very hot stuff, boom, it explodes. This is the debris of an explosion like that. So this is one of the first collisions at RHIC in the year 2000. This is a photograph of that collision taken by one of the cameras. It's a camera that's a detector named STAR. What happened here is that a gold nucleus was going into the screen from us into the screen. A gold nucleus was coming out of the screen towards us. They collided right there in the center of the picture, and the debris had about several thousand cousins of the proton flying outwards from this debris. I'm not going to show you lots of pictures of RHIC because we're much closer to Geneva here. The experiments in Geneva are done at the Large Hadron Collider. You may have seen pictures like this before. This is a satellite view of the city of Geneva. There's the airport. Here's Lake Geneva. The Large Hadron Collider is in a tunnel 27 kilometers around underneath the countryside of France and Switzerland. Here's another cartoon based, well, it's a cartoon drawn on top of a photograph taken from an airplane. And there are bunches of, let's say, lead nuclei whizzing around this tunnel in one direction and the other tunnel in the other direction, and they collide in 4 places where there are cameras located. The 4 cameras are called LHCb, Atlas, ALICE, and CMS. If you can go in the tunnel, this is what the accelerator looks like. You saw this in Carlos's talk yesterday, if you were at Nerd Night. The cameras are amazing pieces of technology. These cartoons don't do them justice, but they give you a sense of scale because there's a person. This is the kind of camera that takes pictures like what I just showed you. It doesn't sound so hard, but now let me tell you, these cameras take about 100 million pictures per second. They generate petabytes of data in the blink of an eye. So this is big science, not only in terms of the size of the camera, but the size of the data sets. This is big data at its biggest. This is an actual picture of the photograph of the camera. This is the Atlas camera, which, by the way, CMS, the C stands for compact. This is the compact detector. This one is even bigger. There's a person right there in the cartoon. That's the real thing. This is LHCb. The group here in Santiago de Compostela is responsible for some aspects of the construction of this camera. You should ask one of them to give a public lecture describing what they've done, they and their colleagues have done, and what they have seen. And then this is the 4th camera called ALICE, and that 4th camera took this picture. So this is a photograph of a collision. This is the debris from the collision in which 2 lead nuclei collided, and there's about 30,000 particles in the final state. So this is a traffic accident where 2 nuclei come in, slam into each other, and 30,000 particles come flying out. An enormous number of these kinds of strings got broken into smithereens. Here's some more photographs from 3 of the cameras. And I'll just point out that something strange seems to have happened here. There's a jet of particles along with along with the 30,000 particles, there seems to be a jet of particles coming out there. I wonder what that is. We're going to have to come back to that. So understanding what quark matter is actually like, how it behaves, had to wait until scientists reproduced it. And these collisions, as I've said, really are making little droplets of the hot Big Bang matter. But what we see in the pictures is not trillion-degree hot matter. We see the debris of the explosion, so we have to do some archaeology. We have to learn how to look at the debris and figure out what was the stuff that exploded like. So how can we learn about the behavior of the hot matter that was there at the very beginning of the collision? How can we learn about it, and what have we learned? Well, I've set you up for this by questioning the gas assumption throughout. What we've learned is that it's not a gas, it's a soup, it's a liquid. This was established by 2005 by Rick in New York. And this was done by looking at how asymmetric blobs of hot Big Bang matter explode. And I'm going to show you how this works on the next 2 slides. But what these experiments revealed is that trillions of degree hot matter is a liquid. This is Rutherford in reverse. Okay? Rutherford was looking for putting an unexpectedly found point-like nuclei. Friedman, Kendall, and Taylor unexpectedly found point-like quarks. Given those 2 pieces of history, everybody expected a gas of point-like quarks. The surprise here has the opposite character. People were looking for hot gas and found a hot liquid. It's not called a pudding. It's more like it's a soup, not a pudding, perhaps. But again, it's very much the exact opposite kind of surprise as the first 2 surprises. There is a way of quantifying how liquid-like a liquid is, and it has to do with, as a liquid, say, flows around a corner, how much internal friction is there, how much dissipation is there. The more friction, the more dissipation, the worse a liquid it is. This has to do with viscosity, and there's a parameter which is, unfortunately, it's called eta over s. Eta is a Greek letter, s is a Latin letter. And I can't help the fact that that's what it's called. This parameter quantifies how much internal friction is there in a liquid. And it turns out that quark soup is a better liquid than almost all other known liquids, possibly except one. And it's this discovery that this liquid, this stuff, what does it mean that it's a liquid? It means that its constituents are always bumping into each other. They're very, very strongly connected to each other. Everybody is connected to their neighbor in a way that is not true in a gas. And this has made it interesting to a broader scientific community because it turns out that this is sort of like the way electrons behave in some of the most interesting materials in material science and condensed matter physics. So how was this discovery made? How was the anti-Rutherford discovery made? It was not made in the way that Rutherford made his discovery. And I'm going to tell you how it was made by taking what appears to be a complete tangent. Because the one terrestrial fluid that is almost as good a liquid to quark soup, I should have said, by the way, somewhere on a slide I said that this stuff was called quark-gluon plasma when people thought it was a gas. We still call it QGP, even though we now know that it's actually not a gas at all. It's not a gas-like plasma. It's a liquid, but it's still called QGP. I'll slip into that sometimes. The one material that is almost as good a liquid is 10 to the minus 9 degrees hot instead of 10 to the 12 plus 12 degrees hot. It's 20 orders of magnitude colder. It's a cloud of trapped atoms. And here's a picture of experiments done in 2010. This is actually a photograph of a cloud of trapped atoms. This is maybe a centimeter in size. So this is it's about 1 centimeter in size. And it's a cigar-shaped cloud of atoms. And there, you now turn off the trap. you let this blob of atoms explode. Now, what would happen if that blob of atoms was a gas? If this were a gas, in this gas, every atom is going in a random direction, and when it explodes, it will explode just as much up to down as right to left. That's not what happens. You can see in this sequence of pictures that this blob of stuff, when it exploded, it blasted left to right with much more force than up to down. It hardly expanded up to down. And this is how a liquid would behave, because for a liquid you would say, oh, I have a liquid here. It has the pressure is biggest in the middle. What drives an explosion is pressure gradients. The pressure gradients are biggest left to right. This is going to explode left to right more than up to down. That's how liquids work. And you can then quantify this. The intuition I just gave is formalized in what's called hydrodynamics. Hydro is water. It's the dynamics of water, or this liquid, or any liquid. And you use the equations of hydrodynamics to pull out from data like this that the eta over S, that parameter that says how to good of a liquid it is, it gets down to around 0.4. And now you look at collisions from the LHC. So I'm showing you collisions from the LHC. This was first done at RIC. Hey, look at this. This is the debris from the explosion. This looks pretty circularly symmetric. And the first one I showed you was circularly symmetric. But look at this one. Or look at this one. There's a lot more force this way than this way. How did that happen? If what you had was a hot gas, that could never have happened. This tells you that what exploded was a liquid. You can just see it. Once your eyes are trained, you can just see it. Oh, but then you have to ask, how did you make a cigar-shaped blob of hot liquid, hot Big Bang matter? Well, when two lead nuclei collide off-center, think of two disks colliding off-center, the collision zone is shaped like my hands are showing here, like an almond. So this was an almond-shaped blob of Big Bang matter, which blasted with greater force this way than this way. That's how the discovery was made. And when you do this quantitatively, you find that this parameter that says how good is the liquid is somewhere around 0.1 to 0.2. That's the lowest known in nature. Water is between 1 and 10. Any liquid you've ever experienced in your life is in this sort of 1 to 10 range for this parameter. Those cold atoms are at about 0.4. This is 0.1 to 0.2. Gas in this room is much more than 100 for this. This parameter is much more than a value of much more than 100. So quarks and gluons in hot soup are not free. They're not a free gas. But they're also not confined into protons. So what we have in the early universe, when it was a microsecond after the Big Bang, is not protons and neutrons. So the expectation was half right. Okay? It is not protons and neutrons. It's a soup of quarks. But it's not a free gas of quarks. It's nothing like a free gas of quarks. The quarks and gluons are not confined into protons, but they're also not free to go to fly independently. They're always bumping into each other. They're always strongly coupled, strongly correlated. These are all words that mean the same thing. I'm going to skip the aside at the bottom of the slide. It's a connection to string theory that's remarkable. This is the second time I've had to skip something that could be an entire lecture of its own. So I think I'll also largely skip this. There's a beautiful analogy between the Big Bang and the little bangs. The Big Bang, this is the universe at age 400,000 years. These fluctuations are observed with telescopes. These are actually simulations. These are not data, but these are simulations of little bangs. We only have one universe to look at. There it is. We can make 1 billion collisions in a month easily. So you can study lots and lots and lots of little bangs. You can only study one Big Bang. In both cases, you quantify the fluctuations, and as you quantify the fluctuations, you find that you can describe the data beautifully. That beautiful description tells you both about the properties of the fluid and about the initial state. In cosmology, it tells you about the proton to photon ratio in the fluid and the initial fluctuations at the very beginning of the Big Bang. In heavy ion collisions, it tells you about the viscosity, the 8/s of the soup. And it tells you about the shape of the nuclei that collided and their lumpiness. I want to, before continuing, I want to quote an esteemed colleague of mine whom I had the privilege of meeting very late in his life. I arrived at MIT in 1997. Vicky Weisskopf was an old man at the time, but I did have the privilege of meeting him. Vicky Weisskopf was the director of CERN in the mid-1960s, professor at MIT for many decades. And in 1977, he was giving a lecture which he then turned into a paper called About Liquids. This was sort of an homage to liquids. It was also an homage to Edward Purcell, who was being honored that evening, and Edward Purcell had done work on liquids. And Vicky decided to honor Edward by speaking about liquids. And I want to read what he said. So the existence and properties of solids and gases are easy to understand. Liquids are harder to understand, 1977. Liquids are harder to understand. Assume that a group of intelligent theoretical physicists had lived in closed buildings from birth such that they never had occasion to see any natural structures. Oh, and let's forget that it may be impossible to prevent them from seeing their own bodies and their inputs and outputs. But let's lock up intelligent theoretical physicists in a closed room, give them the laws of nature, and ask them, what do these laws of nature describe? That's what Vicky was saying. What would they be able to predict from a fundamental knowledge of the laws of nature? Vicky Weisskopf in 1977 said they probably would predict the existence of atoms, of molecules, of solid crystals, metals and insulators, of gases, but most likely not the existence of liquids. So to me, this is a remarkable statement in 1977. Vicky Weisskopf didn't know it, but he was right on. The closed room is called the planet Earth. In 1973, all the physicists on the planet Earth were given the fundamental knowledge of the laws that govern quarks and gluons. They had 30 years to try to calculate what those laws predict. None of them said that hot quark soup was a liquid. They had 30 years, none of them said that. It took experiments to reveal that. So this is a good object lesson, both on the importance of experiments and also for theoretical physicists in the room on the value of thinking outside the box. Nobody actually, this is all seen as obvious today, but nobody saw it as obvious until the experiments made it obvious. So, what next? We're now in the early 2000s, and we've made this great discovery. By recreating droplets of the matter that fill the microseconds-old universe, we, the experimentalists, have, what have we done as of the early 2000s? Recreated the droplets of the first liquid that ever existed. It's the original liquid. It's the liquid from which every proton in today's world formed when the universe was 10 microseconds old, and this primordial liquid fell apart into a mist of protons. And that's what's being reproduced in every one of these collisions. It's the hottest liquid that has ever existed. More importantly, to me, I would say, is that it's the earliest and first complex form of matter. Gases are easy to understand. Vicky Weisskopf said liquids are hard. This is the first and earliest complex form of matter. It's the most liquid-like liquid that's ever existed. It is, in a sense, the simplest form of complex matter because it's very close to the fundamental degrees of freedom of the Standard Model. And all great discoveries, just as all fundamental the discovery of fundamental laws of nature open new vistas. Great experimental discoveries open new vistas and pose new challenges. Two kinds of what next questions for the coming decade. One, in the interest of time, I will go briefly over. One is, what is the phase diagram of this matter? When in the late 1980s, experiment discovered high temperature superconductors, you ask, as a function of temperature and doping. Doping is excess of electrons over holes in a material. What are the phases of matter? We ask a similar question as a function of temperature and doping. Doping for us is excess of quarks over antiquarks. What are the phases of matter? These are cousins of the proton. Whoops, sorry. This is ordinary matter. This is near and dear to my heart, as Carlos mentioned. This is the superconducting quark matter, cold quark soup that may be found in neutron stars. This is the hot quark soup that we are talking about. And one of the quests for the coming decade is to ask whether this cartoon is drawn correctly. Is there actually a critical point on this phase diagram? I think we may know the answer from experiments done in New York by next summer, but I'm here this November, so I don't know the answer. So I decided to focus on the other what next question. So the second what next question, and the one that I will spend the rest of the talk on, is a question that we're privileged to have a chance to address because our complex matter is so close to the fundamentals. And that is, how does this liquid actually emerge from the laws? Why was it such a surprise? Okay, now we've had the surprise. We should go back and ask, how do the laws of quarks and gluons that were discovered in 1973, how do they describe a liquid? So that means we need to probe the liquid. We need to see its inner workings. The first step to seeing what those quarks and gluons in the liquid are doing, how are they making up a liquid, is actually just to see them. So we need Rutherford. We need Rutherford for the third time in the evening. We need a way of taking a high-resolution, fast shutter speed look at one quark or gluon at one moment. So we need to do for hot quark soup what Friedman, Kendall, and Taylor did for protons. Well, unfortunately, we can't bring the hot quark soup to Stanford. It's made in Geneva or in New York, and it lives for 10 to the minus 22 seconds. You can't get it to Stanford. So we have to find a probe that is made in the same collision that makes the soup. And this is where jets come in. Jets have appeared twice this evening. When those electrons blammed into the proton, they made a spray of particles, which I call the jet. This, although I didn't highlight it so much, this is a jet also. This is a drop of hot soup that exploded, but this hot soup, there's a jet in the same collision. That's pretty cool. This is a more modern image of an event at the Large Hadron Collider where you made a drop of hot quark soup and two jets, this one and this one. And this one looks a little more beefy, this one looks a little more feeble. So what's happening here? What's happening is that in the same collision that made the hot soup, which is here the blue blob, right at that red star, in the collision, a quark coming into the board and a quark coming at you and a quark going into the board collided with such force that they were kicked in the way, same way that when the electron kicked my hand and created a jet of smithereens, now I have a quark kicking a quark and making two jets of smithereens, one going this way, one going that way. But these jets of smithereens now have to fight their way through the soup, and all of a sudden we can do a Rutherford experiment, at least in principle. Because we can ask, well, maybe as this spray of particles is going through the soup, maybe somebody gets kicked to the left at 45 degrees. That would be like Rutherford. But there's another thing that we have to take into account, and that is that, I should say it here. There's another thing that we have to take into account, that when you shoot a bullet through water, it makes waves. Okay, and so when you shoot this jet through a droplet of hot liquid, it makes waves. So there's two phenomena that we're interested in. One is very liquid-like. The waves in this jet is going to make waves in the liquid. It's a bullet shooting through a drop of liquid. It will make waves. And the other is very Rutherford-like. One particle in this jet might scatter at 45 degrees. And I've just tried to give you a cartoon sense that jets in heavy ion collisions are not easy to understand. There's many different kinds of complex dynamics occurring when a jet goes through a droplet of hot quark soup. It will not be easy to decode the wealth of information that's hidden inside the data. And what theoretical physicists are doing today is to use today's data to build a baseline of understanding. The cartoon is easy, actually, to describe. Jet quenching, by the way, this phenomenon was discovered at RIC, but it's much, much easier to see at the LHC. At the LHC, you find events where this spray of particles has 200 GeV in energy, whoops, and this one is only 70. Where did all the rest of the energy go? Well, it went into the waves. In this cartoon, you can see this jet had to go through a lot more blue liquid. So this jet made a lot more waves in the liquid. It will come out feeble. And when you see the actual data, this was the jet that went through more liquid and made more waves. Seems easy, but it's actually quite hard to do this quantitatively. But nevertheless, this is, I think, the key direction for the next decade. On this slide, I've given a list of examples of the kinds of things that theoretical physicists, including people in this room, have been doing to prepare for the next decade. I'm going to briefly speak about one example, which is how can we identify the ways that experimentalists should separately look for the waves and the Rutherford. I'll briefly do that on the next slides, but before I do, the next several years will in fact be the golden age of this physics. The physics of probing the quark-gluon plasma, that's what's coming next in this subject. The Rutherford experiment hasn't yet really been done, but it's coming. It's coming in New York. There's a new camera called S-Phoenix that was designed to do this experiment. In the Large Hadron Collider, runs 3 and 4. Run 3 just started. It's the next few years. Run 4 is later in the decade. There are new theory advances. And the group here in Santiago de Compostela is one of the world leaders in this. And I'm going to ask at this moment everyone in the room who works on probing quark-gluon plasma to stand up. So that's certainly Carlos and Nestor and Elena, but all the students and postdocs also, we'll say you two also because I know you've written one paper on probing quark-gluon plasma. Everyone here in Santiago who's working on probing quark-gluon plasma, please stand up. Stand up, stand up. Students, postdocs too. There we go. Stand up, stand up. There's actually more. People aren't standing up. There's more. So why did I come to Santiago? To give this lecture, yes, but to talk with these folks. And any one of them could give the next lecture. Okay, you can sit down. So this is one of the world centers in this activity. But I will say the person whom I've learned the most about jets in heavy ion collisions from did not stand up in this room. His name is Danny Pablos. He's the person I've learned the most from. And the thing is, Danny Pablos is coming to Santiago in January, so you'll have him too. The next few slides are for the experts only. I'm just going to say something that Danny Pablos has done recently with me. This is to give you a sense of, can you actually see Rutherford? Could you do a Rutherford experiment? These are predictions with no data. This data can be taken next year at the LHC. These are experiments where you look at a photon back-to-back with a jet. If there's no Rutherford scattering, you get the blue and black curves. If there's Rutherford scattering, you get the red and green. It's a big effect. You can dial a setting on the camera and make it go away. So you have control over whether you look for Rutherford scattering or you avoid looking for Rutherford scattering. You can also dial another setting on the camera and look for the waves in the fluid. The difference between blue and green here is the effect of waves in the fluid. And I just dialed so this camera at the Large Hadron Collider has settings, which I'm not explaining, but for the experts, ask me afterwards. It's possible, and these are all these curves are predictions using parameters for the setting of a camera called CMS. And the CMS experimentalists tell us that they can make these measurements next year. So with the cameras that exist in Geneva, you can look for the waves in the liquid with one setting of the camera. You can look for Rutherford with a different setting of the camera. These are slides for the experts. But now back to my closing remarks for all of you. So first I'll just repeat. I've just sort of teased you with a sense that there's a Rutherford experiment to be done. It's the third Rutherford experiment of the evening. It will happen starting next year at the Large Hadron Collider in Geneva and also with S-Phoenix in New York. The last thing I wanted to do to close the talk was to come back to protons. So what have we learned in the second half of the talk? We've learned that the essential feature of the laws of nature that govern quarks, if you ask how does quark soup behave, the answer is it depends. There's no one answer. A droplet of it flows like an extraordinarily liquid-like liquid. But if you photograph it Rutherford style with a fast shutter speed and high resolution, you'll see quarks and gluons inside and look at its inner workings. So depending on how you look at this hot quark soup, you either see quarks and gluons or you see a liquid. And amazingly, protons are the same. I stopped the story of protons way back in 1973. There's another story that someone else can give another evening on 50 years of taking photographs of protons. 50 years of what Friedman, Kendall, and Taylor started. 50 years of electron scattering. And people have learned how to vary the shutter speed and vary the resolution. And how protons look depends on your shutter speed and your resolution. This is hard to depict. And very recently, 2 scientists and 3 artists spent several years building an animation that I'm going to show you right now that with some artistic license is a way of depicting what we've learned about the structure of the proton and how it changes depending on how you look at it. So Richard Milner, Rolf, and James LaPlante, who's an animator, and 2 documentary filmmakers made this animation. I'm just going to play it and I'll talk over it. Oops, sorry. That spoiled the punchline here just a minute. That's the end of it. So this is what the proton looks like if you have a slow shutter speed. And if you have a pretty bad resolution. And now as the yellow bar is moving left to right, the shutter speed is getting longer, but the resolution is still bad. And it sort of looks like there might be something interesting going on, but now we're going to dial up the shutter speed. So now, very, very fast shutter speed and very good resolution. Sorry, now we dialed up the resolution. So this is very fast shutter speed and very good resolution. And now slow the shutter speed down, but keep the resolution high. And what you see is what I was doing with the rubber band. But you only see it if you look in the right way. If you decide that you want to look with a fast shutter speed, but right there. That's fast shutter speed and very, very high resolution. You don't see the rubber bands. You see a soup. So that's the best we have to date at visualizing what a proton actually looks like. And you see how amazingly similar it is to what we've learned about hot quark soup. The answer is it depends. It depends on the resolution and shutter speed of your camera. And remember that every proton in the universe today formed from hot quark soup. As the primordial liquid, the hot quark soup fell apart into a mist of droplets, a mist of protons, 10 microseconds after the Big Bang. Every proton around us today came from hot quark soup. Yeah, they're not hot anymore. They've had 13 billion years to get cold. But don't they still look a lot like the primordial liquid from which they were born? That, to me, is one of the very interesting puzzles for the 2030s. In the 2030s, this story will come in a full circle. In the 2030s, the next great accelerator will begin taking data. It's being built outside New York again. And it will image the proton with a range of camera settings that have never been possible before. So I'm going to end by saying let's look forward to surprises. Perhaps protons actually are hot quark soup. Maybe when we learn how to take pictures in the right way, suppose that we see that inside protons, that cloud was actually swirling with orbital angular momentum. That would be a lot like the flow of the liquid that we've discovered in the 2000s and 2010s. We don't know if that's so. The camera to tell us is being built right now. So our journey has taken us from protons to the hot Big Bang and back. Rutherford saw nuclei in atoms, and then Friedman, Kendall, and Taylor saw quarks in protons. This was all understood by Gross, Wilczek, and Politzer exactly 50 years ago. Understanding these laws opened new doors. It opened doors to asking about cold quark soup in neutron stars. There's a question mark there. It opened doors to asking about hot quark matter in the Big Bang. There's an exclamation mark there. We know that the Big Bang was filled with hot quark soup. It's been reproduced in the laboratory for the last 23 years and studied. It turns out to be the most liquid-like liquid that we know in the universe, the simplest form of complex matter. And this decade, we can repeat Rutherford's strategy to see its inner workings. That's what's coming very soon, and Santiago de Compostela is leading the way. And next decade, back in New York, the descendants of Friedman, Kendall, and Taylor will have an extraordinary new camera to look with which to look at the proton. And maybe it will turn out that this vision that I've ended the talk with, that protons are the littlest droplets of hot quark soup, maybe that will turn from metaphor to science. We will see. Thank you. Carlos, should I take questions? I'd be happy to. Well, the microphone. Oh, yeah. They want the microphone. But why don't you raise your hand so that when the microphone comes, they know where to. Here it is.
Okay, so thank you very much, Krishna, for this incredible talk. So, questions? ¿Ustedes preguntas? Si alguén non ten ganas de facer a pregunta en inglés, podemos traducir tamén, vale?
Oh, you'll translate.
Yes, well, we can make the translation if needed.
Yep. I apologize that I don't understand either Galician or Spanish. Although I will say that at Nerd Night yesterday, I understood science in both Spanish and Galician, which, as I said last night, means that the language of science is universal, but ordering a cup of coffee is harder. Questions? There's one over there on the left. Carlos, we need your son. He asked a very good question of you yesterday.
He's studying. He has an exam tomorrow.
Okay, so first of all, thank you very much for the talk. It's been very enlightening. And I wanted to add a question about this quark soup.
Yes.
And how you said that it behaves like a very good liquid. And I suppose that has to do with the properties associated with liquids. How can you measure them? Because you said this quark soup lasts for very few quantity of time. How are you able to measure them? Are there any theoretical models or any experimental results?
Yes. So the way you measure it is by looking at the debris of the explosions when this soup explodes, a drop of the soup explodes, and quantifying. I did this obviously qualitatively, but you quantify the you have to take a hydrodynamic description. So the theory is called hydrodynamics, and you have to use your hydrodynamic description to describe how an initially almond-shaped blob of quark gluon plasma explodes, and how it explodes with more force this way than this way. I don't have slides with equations. It's obviously possible to describe this with equations, but that's the essence of how it's done. And it's actually easier to understand with this other example where you can see this blob of liquid explode in a way which is very asymmetrical. What I will say is that there are other properties of liquids that we are not yet so well able to measure. There are two kinds of viscosity. There's shear viscosity and bulk viscosity. The shear viscosity now we know very well. The bulk viscosity we have a more cloudy view of. The other thing that we don't know is its surface tension. It would be wonderful to be able to measure the surface tension of a liquid. That's a property of a liquid that is measured all the time for water, let's say. The reason it's not is how do you measure it? For the surface tension of water to make sense, you have a drop of water and it's sitting there. And you can sort of poke the surface and watch how it ripples. We don't have a drop of quark-gluon plasma sitting there. The thing explodes. So the only way we could measure the surface tension would be if we had some way of having a drop of hot Big Bang matter with other stuff around it, holding it in and keeping it still. Okay, that's impossible. Cold quark matter, though, cold quark matter in neutron stars, if we are so lucky that a 2 solar mass neutron star it's about 10 kilometers in radius. Let's say the inner 5 kilometers is cold quark soup. There's now a surface. Okay, there's a surface at 5 kilometer radius. And people have tried to calculate the surface tension of that surface. Unfortunately, I don't know any way at this moment of measuring it because we don't even know whether neutron stars actually have quark matter. But in the case that I just described, there is a surface tension. It's calculable. It's a long way from being measurable. So surface tension is an example of a property of this liquid that we don't have a good path toward measuring. So maybe you can find one.
Maybe. Thank you.
More questions?
First of all, thank you very much for the awesome talk. And I wanted to ask about something you said earlier about that the GDP, the soup being actually
call it the soup.
A liquid was a surprise. And I was wondering if it isn't somewhat predictable in the sense that you know that the interaction between quarks grows large at some point.
Yes.
So they cannot actually roam free like in a gas.
Well, so absolutely it should have been predicted. So if you ask me, should it have been predicted? Yes. It's not quite as easy as you said. And the reason is that at the temperatures we're talking about, and by the way, I didn't say it, the Large Hadron Collider achieves droplets with about 10 trillion degrees temperature. Maybe 6, 7, 8, 9, 10 trillion in that range. At those temperatures, the density of quarks and gluons is so high that they are never really far apart from each other. But they're moving very fast and bumping into each other very hard, and people thought that it should behave like a gas. In point of fact, it turns out that even at these densities, and even when they're moving as fast as they are so much always bumping into each other that it's even hard to define the answer to the question of how far does each quark travel between bumping into one thing and the next. It's like it's always bumping into things. With hindsight, it feels obvious. But I will say, so look, in 1973, when my thesis advisor, Frank Wilczek, and his colleagues, Gross and David Politzer, discovered these laws, I was in elementary school. I was 8 years old. So in terms of the 30 years of theoretical physicists having the laws and not predicting the liquid, I'm not responsible for the first part of the 30. I first started thinking about this physics in the mid-1990s. So I had about 5 years, and I didn't realize it was a liquid. And I think partly the reason for this is that we weren't asking the right question. Until these experiments showed stuff like this, people weren't asking the question, is it a liquid? And it turned out to be the most interesting question of the first The most interesting question for the next decade will be about jets, I think. But for the most interesting question for the period between 2000 and 2005 was, is it a liquid? Answer, yes. Nobody was asking that question in 1995. It's kind of a little bit similar to Friedman, Kendall, and Taylor. Post facto for us today, it is so damn obvious that the right experiment to do was shoot an electron at the proton, look for large angle scattering. It's just like Rutherford. That's how you'll see the quarks. But I'm telling you, I wasn't there, but when you talk with people like David Gross, who was there, Jerry Friedman is someone that I know pretty well. Also, Henry Kendall, I met before he died. Nobody was asking the right question. And so there's a thing that happens this is about a community of people. Scientists are people. And when you have a community of people, you talk to each other, you drink coffee together, maybe you drink beer together, we're going out for dinner this evening. A common view develops. And sometimes that's really a good thing. Okay, we learn from each other, I'll learn from him, I'll learn from him. That's why I come to a place like Santiago. And that's a good thing. But sometimes the result is that we all think we know what the interesting questions are, and we miss one. And there are two examples like that in my talk.
Thank you very much.
So I will say, for the young scientists in the room, it is really, really important to think for yourself and to ask iconoclastic questions, questions that are your own, but do not make the mistake of only doing that, okay? You better understand what everybody around you seems to think is interesting. Make sure you understand that. Don't ignore it, because you can make contributions by advancing science within the view, by thinking about the questions that people around you all say, oh, these are the interesting questions, you should think about this. Yes, think about that, but don't only think about that.
Good advice. So, more questions? Oh, Jose here.
Jose.
Thank you. Do you expect that inside a neutron star, if you go all the way down to the center, I don't know, maybe the quark gluon, the gases would come out, or some other state of matter?
Well, okay, so so the people you should ask to give what's next year? Next year is Science Week 7. Okay, for Science Week 7, you should ask Alexei Korkula to come and speak about that question. He's an example. There are others. Alexei Korkula is someone that Carlos knows, and if Carlos invited, I'm sure he would come. So what I'll say is this. I am absolutely convinced that if you can crush nuclei to 20 times their density, what you will have will be a cold quark matter, which is a color superconductor. The quarks form pairs, Cooper pairs, and you get superconducting QCD currents. This is what I wrote many papers on when I was a beginning professor. And this is one of the talks I didn't give today. But then you ask, well, okay, that's 20 times density, 20 times nuclear density. What if you did 10 times? What if you did 5 times? Well, at some point I say, I don't know. And okay, now you ask about neutron stars. Neutron stars, the most common garden variety, it's an amazing thing to say garden variety neutron stars, but the most common garden variety neutron stars are about 1.4 times the mass of our sun. Those probably have central densities only in the range of 2, 3, 4 times nuclear matter. But there are known neutron stars that are twice as heavy as the sun, and those might have densities as large as 10. So what Alexei Korkula and his colleagues are doing is to try to put everything we know together from the physics of quarks, the physics of nuclei, the physics of neutron stars, gravitational waves, measurements of neutron star radii, and if I look at their results with optimistic glasses, it looks like 2 solar mass neutron stars have quark matter cores, but nobody is going to say that in a way such that it goes on the front page of the newspaper. It is not yet demonstrated rigorously, but it's getting It's getting more and more. It's getting it's looking more and more like that. And if that's the case, if you have a soup of quarks, it's a color superconductor. That'll be one of the most exciting discoveries in my career, based on the things I've done in the past. But it's a big if at the moment. So if you know how to make matter that's just a little bit denser, that'd be great.
Yes. Unfortunately, you cannot make neutron stars much larger than that, because then
you get a black hole instead.
Boring black hole.
You get a boring black hole instead.
That Jose likes. Okay.
By the way, for those of you interested in boring black holes, I have many friends at MIT who work on LIGO. The next science run of LIGO has started, and what I hear in sort of hallway, corridor chit-chat mode is that LIGO has seen now 2 black holes merging into each other and emitting gravitational waves. This won the Nobel Prize, what was it, 3-4 years ago? Okay. What year was it? What year was the discovery? 2017. LIGO is now seeing about 3 such events per week. So, which is amazing. They haven't yet started showing the data, but that's what they're seeing. And now we have to hope that they'll see every few weeks 2 neutron stars merging. That won't be many per week, but that might be 1 a month. And then we're going to really start learning stuff. But the last time I heard from my friends on LIGO, they didn't say yet that they had a growing catalog of neutron star events, but they're seeing lots of black holes. So for those of you who do black hole physics, there's now statistics.
Okay, so more questions for Krishna? This is your last chance.
In the back? I can't see the back, but raise your hands high in the back if you've got questions. Oh, there we go.
There.
And there is one.
Very
there.
good.
Very good. Thank you. Thank you to whoever did that with the lights.
You talked about these tiny droplets of hot soup,
Yes.
hot quark soup, and you said that they explode very quickly.
Yes.
My question is, why and how do they explode?
So why do they explode? I need 2 hands. It's hard to talk with your hands when you've got a pointer in one hand. When 2 nuclei collide like this, you make this blob of very hot stuff. But there are no walls around it. And so I've got this extremely hot, very high pressure blob, and the high pressure blows it apart. High temperatures are associated with high pressures. If you take the class that I teach at MIT to second-year undergraduates, you'll learn that high temperatures are associated with pressures that are proportional to temperature to the 4th power. So high temperatures make very high pressures. And so to prevent, the question is not why does it explode, it's is there any conceivable way to prevent it from exploding? There's this enormous pressure. For you to stop it from exploding, you would have to put walls around it that could withstand an enormous pressure. And there are no such walls known. So it explodes. Now, if we look at it this way, if the droplet is circularly symmetric, then it will explode in a circularly symmetric way. If the droplet is shaped like this, it will explode asymmetrically, and that's what's shown in the data. So in terms of how it explodes, there are other ways of answering the question, but the best way is what I just said. And thank you.
Okay, some last question.
Yeah, again in the back. Let's privilege the back at this point.
First of all, thank you very much for this awesome talk. I have 2 questions in one. The first one is, you talk with the Jim rubber that there is no limit when you separate it with this energy between the quarks, but I want to know if when it's the maximum limit of this energy, when you make it together, the energy is maximum when it's the minimum the distance. And the second one is, I don't know, but I would start the answer with, if there is extra energy when you broke this this energy between the quarks,
Yes.
Could it be dangerous to achieve, let's say, a quark bomb?
No.
I don't know.
Well, I think the answer to the second question is no, because the total, when you collide two nuclei like this, the energy densities are enormous, but nuclei are very small. So the total energy in one of these explosions here, if you had a way of making a blob of this stuff that was this big, like I'm showing my hands, that would be an inconceivably large amount of energy, okay? But the blob that exploded there was 10 to the minus 14 meters across. So instead of 10 centimeters across, it's 10 to the minus 12 centimeters. It's about 1/10 trillionth smaller than this. And yet it made thousands of tracks. So in one sense, it's a lot of energy, but in another sense, relative to human scales, it's actually not a dangerous amount of energy. So this answer to the second question is an easy no. Your first question was about the breaking of the rubber band?
Yes.
Could
No,
you
I
say it
mean, there is no minimum limit when you separate the
when they
quarks.
get close together.
Yeah, it's a maximum energy, and, when you achieve this maximum energy.
So good. This is a very good question. So
Thank you.
When two electrons get closer and closer together, the force between them grows like 1 over distance squared. And when two quarks get closer and closer together, the force between them grows, but more slowly. But it does grow. It grows. I'm not sure how familiar with math you are, but it grows like 1 over distance squared. But the prefactor in front of it decreases logarithmically, and you can ignore that if you don't know what I just said. But it grows more slowly. Now, why does that mean it's weakly interacting? And the way to say that is actually to let's ignore everything I just said and think about a gas. Okay. Suppose we had a gas of quarks versus a gas of electrons. As you make the gas higher and higher density, the interaction energy goes up because the electrons are close together, the quarks are close together. But in order to make it higher density, in quantum mechanics, you also have to make the momentum of all the particles higher. And it turns out that with 1 over r squared force law, those two effects scale the same way. Whereas if you have a force law like for quarks, as you make the gas denser and denser, the interaction energy grows more slowly than the energy of motion. So I skipped all this. So you found a good question. But this notion that what Gross, Wilczek, and Politzer found corresponds to weak interactions when quarks are close together can be quantified in the way that I just tried to describe with my hands, but I hid from you in the talk.
Okay, thank you very much.
Okay, so very last chance. Otherwise, we can. Oh.
Well, in fact, I had 2 questions. The first one is like more superficial, let's say. It is, why was the word color in particular chosen for speaking about quarks?
Okay, what's your second question?
And the second question is, wait, I forgot it.
Okay, well, so I'll stick with the first question then. So the answer is, the first part of the answer is that the name color was chosen in the mid-1960s, and I was born in 1965, so I can claim no responsibility. In this period, basically between the mid-60s and the mid-70s, the basic facts of how quarks behave were all figured out. And people had to name things that were not familiar from everyday life. First of all, quarks themselves. Why were they called quarks? That was Murray Gell-Mann named them, and he famously said, well, there seems to be 3 quarks in a proton, and there's a line from Finnegan's Wake, a book by James Joyce, which is 3 quarks for Muster Mark, and Murray Gell-Mann liked Finnegan's Wake, so he named them quarks. So there's no reason at all. It's just that Murray Gell-Mann named them quarks. George Zweig named them aces. The same thing. George Zweig and Murray Gell-Mann both realized that there was these patterns that could be explained with what we now call quarks. George Zweig called them aces. Quarks stuck. Okay, there's 3 kinds of quarks, up, down, and strange. Well, that's actually, strange was called strange because up and down, I don't know why they're called up and down necessarily, but they were named first, and then the strange one seemed strange, so it was called strange. That's actually understandable. But then the next one was called charm. Why that? There's no answer. The next one was called, some people say bottom, some people say beauty. No answer. Some people say top, some people say truth. No answer. So people had to give names to things, and they picked words that had no correspondence to the things that they were naming. Color is an example of that. There's the one defense of the people in the 1960s who chose the word is that there are 3 different colors, and they said, let's think of them as red, green, and blue, and red light, green light, and blue light makes white, which is colorless, and there's an aspect to color which is that the 3 colors add up to colorless. So that's probably the answer. I will say, speaking as someone who did not live in the 1960s and who in the 1970s was this high, there are people I know who look back at their predecessors from that period and speculate about what they may have been smoking. But we will not, we don't know.
And I have just remembered the other question. There were several moments during the talk where you refused to explain other topics that
yes. I didn't refuse, I just didn't have time.
Well, but there was one introduced in the picture by the word aside that yes. I was particularly interested about.
Okay, there's 2 experts right here, okay? Jose or Javier could come up here and speak for an hour about the holographic duality that I had in an aside. This is a theoretical discovery made by string theorists like Jose and Javier are two people from the string theory community. In fact, the key discovery was made by one of his undergrad buddies named Juan Maldacena. And what a whole set of people whom I wasn't paying attention to when they were doing this work in the period, let's say 1997 to 2000, what they discovered is that you can have exactly the same physics described in 2 ways, and it's the same physics. One way is to say I've got a hot soup in a 3-dimensional world, 3 dimensions like our world, and it's a hot soup. It's not exactly quarks and gluons. It's a similar theory. It's not the same, but it has many similarities. And over here, there's a 4-dimensional theory with a black hole in it. And over here, you do calculations the way Einstein taught you to describe black holes. And over here, you're trying to do calculations like what I'm talking about to describe hot soup. And unfortunately, unless Jose and Javier have a new discovery that they haven't told me about, no one has shown that they can do this for the theory that Gross, Wilczek, and Politzer discovered in 1973. What we all know how to do is to do this for theories that are similar but not the same. So there's a catch. But for these similar theories, you can do amazing things. You can do calculations over here in this picture that are easy, that answer questions that nobody has ever figured out how to calculate yet in this picture. And so I could go on. It's an entire talk. But one of the examples is this 8/s parameter for this soup. You calculate over here by looking at a very simple calculation of the physics of black holes in 4 dimensions. Sounds crazy to someone like me, although I learned how to do these calculations in around 2005. So Maldacena figured this out in 97. I caught up in 8 years later. and you find that this 8 over s is 1 over 4 pi. 1 over 4 pi is about 0.08. The experiments say it's around 0.1. 0.08 and 0.1 are very close to each other. So this is one of many ways in which this holographic duality, which Maldacena discovered and many people have exploited, including the 2 characters in the front row here, has been used to teach us interesting things about hot quark soup, albeit not quite in the theory of Gross, Wilczek, and Politzer. Fair? Is that fair? Did I butcher it? I hope it's okay.
Thank you very much.
Ask them to talk about this.
Okay, I think we can stop here. Thanks a lot, Krishna, again.
And let me thank Carlos and colleagues for the opportunity of both giving this talk and visiting Santiago, and all of you for the great questions, including the last one. Thank you.